When your code runs slow, you often blame complex logic or a bad algorithm. But here is the hard truth. Your CPU isn't angry at your software design. It is screaming because you are forcing a sequential processor to hunt for data scattered across its memory hierarchy. In modern AI and machine learning workloads, this random access pattern does not just slow things down, it creates a catastrophic performance cliff that turns nanosecond operations into microsecond delays. Today, we connect that frustration to the physical reality of hardware. We will look at why treating every pointer as cheap is an architectural mismatch for high-performance computing and how you can fix your pipeline by changing where data lives, not just what code runs it. The biggest misconception in engineering is the belief that random memory access is constant time. In textbook computer science, we learn that accessing a linked list node or an array element is O1 operation. It should take forever to wait for one step and then instantly get the next. But on real hardware, this assumption breaks down the moment you cross cache boundaries. Empirical benchmarking of modern systems shows that random memory access behaves much closer to the square root of n rather than constant time as data size grows. When your working set exceeds the L1 cache, which is typically around 32 kilobytes on many processors, latency jumps dramatically from a single nanosecond to roughly 1 microsecond once the CPU must fetch data from main RAM or swap it out. This represents a 100-fold performance penalty caused entirely by cache misses. You are asking your processor to walk across a city block for every step instead of grabbing what is in its pocket. This physical reality creates a shared bottleneck that many developers overlook because they focus on algorithmic complexity rather than data movement costs. Modern multi-core CPUs do not have independent random number generators running silently in the background of every thread. They share a single hardware engine, such as Intel's RGBIC instruction set, which has a hard throughput ceiling of approximately 800 megabytes per second across all cores combined. Quick resource note. I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. When legacy code fails to check the carry flag for saturation under heavy load, threads receive invalid zero values instead of random numbers. This does not just slow your application. It causes silent data corruption because valid entropy is replaced with zeros when that single engine hits its limit. A missing conditional check in a loop can turn high-performance logic into a system-wide stall where the processor waits for an unavailable resource while other cores sit idle or process garbage data. This architectural mismatch becomes critical in AI and machine learning, where hardware relies entirely on contiguous memory access patterns to function correctly. High-throughput systems like GPUs and TPUs are designed around tensor operations that assume your data is laid out sequentially in memory. When software engineering practices assume any pointer is cheap, they introduce the exact friction that causes these accelerators to stall or throttle. Consider video decoding pipelines where non-contiguous data triggers cache misses that GPU acceleration must then bypass. If you feed a model with scattered pointers instead of contiguous blocks, you force the hardware into a state where it spends more time moving data than computing results. The result is an inference pipeline that runs slower despite having expensive silicon sitting idle because the software cannot deliver the fuel at the speed required by the engine's physical constraints. The solution requires shifting your mindset from algorithmic complexity to memory layout strategies. You must stop asking if a loop is efficient and start asking if those data structures are contiguous in memory. A common pattern change involves moving from an array of structures to a structure of arrays, which aligns data so that related fields sit next to each other on the same cache line. This simple reordering allows the prefetcher to load entire blocks of relevant data before you even request it, turning microsecond delays back into nanosecond operations. In practice, this means auditing your data structures before scaling models or increasing traffic. When an AI model runs slower than expected during a deployment, the first suspect should not be hyperparameters or network latency. It is often the way data is stored and retrieved. The fix is rarely more compute power, but rather reordering how you store information to match the physical constraints of SRAM caches and main RAM. Engineering teams that master this distinction build systems that scale reliably under real-world load, regardless of how powerful their GPU cluster becomes. Understanding memory hierarchy is a prerequisite for senior-level system design in AI engineering because optimizing an algorithm is useless if the underlying data access pattern forces hardware into cache misses every single iteration. You can have the fastest processor on Earth, but without contiguous data flow, you are simply building a bottleneck that no amount of raw speed can solve. The industry has already begun solving this problem through hybrid decoders and optimized libraries like libplacebo or DAVD, which offload specific data movement tasks to specialized hardware. These tools effectively realign software logic with the physical constraints of modern silicon by handling memory coalescing at a lower level than standard application code can manage. By adopting these patterns early in your development lifecycle, you avoid the silent degradation that turns well-designed systems into performance nightmares under load. Your CPU is not angry, it is simply operating within its design limits. If you force it to hunt for data scattered across memory, it will slow down or fail gracefully to protect itself from corruption. The difference between a system that scales and one that stalls often comes down to whether your code respects the physical reality of how modern processors actually access information. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.